see.
Mm-hmm.
But soon. And then I didn't go over this briefly, but we are going to talk about the mission heading to Mars a little bit later on too, which should be interesting and exciting.
Perseverance.
There we go. Mission to Mars. If you haven't seen, have you guys seen that movie?
Which movie?
Mission to Mars? No? Okay. Heather Laird is in the comments or in the chat right now, and I made her watch that movie. It's a good one. It's from like the early 90s or so. And It's got Gary Sinise in it.
Well, he's good in most things.
He's good in many things, especially space related things, it seems. Alrighty, well, it's 8 o'clock, so we should get started. Welcome everybody. We are back for our self-isolation star party. I'm sorry I missed the last one. I'm excited to be here with you guys tonight. Ryan is here as per usual. And tonight we have Charissa Campbell with us as well. Charissa is a PhD student at York University, and she studies clouds on Mars. And she's one of the coolest people I know, and I'm really excited to have her here.
Thank you.
She helped us put together the GA last year as well in Toronto, which we hosted at York University. And I'm so excited to talk to you about Mars and everything that's going on.
I love Mars. I'm so pumped. Like, Mars is just so cool. There's so much going on. There's so much happening all the time. We've got orbiters, we've got landers, we've got rovers. We're going to hear about all of it, right? Right?
Oh, yeah,
yes.
Sure.
Yeah, we are.
First, we're going to start off with some space news, though, because some interesting things have been happening in space. Ryan, can you enlighten us, please?
Yeah, it just happened today, actually. A story came out. You're going to see headlines for this over the next couple of days. It is the closest black hole ever discovered, closest black hole to Earth that's ever discovered. And before you start to say, oh no, a black hole is like right next door. No, it's about 1,000 light years away. So don't worry about it too much, first of all. But I guarantee you, every headline that you're going to see over the next 3 days is going to be closest black hole to Earth ever discovered. It is interesting in particular. This is part of a a triple star system in a southern constellation called Telescopium. Telescopium. So I'm actually going to show you where it is. This is the constellation Telescopium in the southern hemisphere, and that little circle right there is showing the particular star. So not only is this a black hole that is relatively close to Earth, it's a black hole that is orbiting a star that's in our sky, a naked eye star. That star is about magnitude 5. So I've actually kind of shown simulated it here in Universe Sandbox. So you can kind of get a sense of what the system actually looks like. The black hole and a bright blue giant star about 5 times the mass of the sun are orbiting one another, orbiting their center of gravity over a period of about 40 days. And that's important because that really small orbital period means it took a long time and a lot of observations to tease out the fact that this star looks like it's orbiting nothing. And you can see kind of in the background that there is a third star much further out, also a bright B-type star, which are hotter, brighter than the sun, a little bit more massive as well. But that black hole is expected to be around 4 or 5 solar masses. So pretty small as far as black holes go, but when you're comparing it to the sun, it's pretty huge. But the important thing about this, one of the important things I should say, is that this is one of the first black holes that's ever been discovered that isn't actively sucking up stuff. Right? Typically, when we find black holes, we find them because they're sucking in so much matter that they're emitting X-rays in all directions, and we can see those from Earth. But this one in particular is important because it gives us a place to look for black holes in our galaxy. And it's estimated that there's up to 1 billion black holes floating around out there in our galaxy, and they might be in systems, triple systems, just like this one. So that was quite the rant. It's fun though. I'm really excited about this, but it's going to be sensationalized over the next few days.
It's still really exciting to have something relatively close by. I mean, I know 1,000 light years is still pretty far away, but it's exciting to have it in our neighborhood in a way, and it is really neat that I have never heard of a black hole being discovered that's around a visible star, like a star that you can go out and see.
Unfortunately, we can't go out and see it because it is in the southern hemisphere. But I thought, I honestly had that moment of like, man, I should really fly to the southern hemisphere and see that, or at the very least, add it to my list of objects to look at in the southern hemisphere, just for that reason alone.
Someday we'll all be able to go down on our trips that we want to go on to see the things that we want to see. But for now, I suppose we will survive with things like Stellarium and maybe a couple of views from other folks who are in the southern hemisphere who can connect with us.
Oh yeah.
That's very, very cool. And then I wanted to throw out quickly, because we have talked about Comet Atlas almost every single time that we've been on. And so I wanted to wrap up the Comet Atlas thread by just showing you guys what it looks like now, or relatively recently. This was a photo taken by Hubble of all of the pieces that it has broken up into, unfortunately. So it was very cool to be able to see a photo that close of it in so many pieces, especially when most of what we can see is just still kind of a bright blob. But it does mean that it's probably going to get a little bit, well, it is going to get dimmer as we go through.
Yeah, it's not going to be the comet of the century. It's sad. I mean, I get my hopes up for every single comet. Actually, here, I've got to share this is the brightness curve of the comet. So basically, this is a graph of my hopes and dreams. What you're seeing is the brightness is steadily increasing through, January, February, March. We get up to about magnitude 7, and that's about where the disintegration starts, and it just starts breaking apart. That red line represents the trend that it was going toward, and you can see it's right around magnitude 0. So it would have been visible to the naked eye in the sky. It would have been absolutely beautiful. But instead, we get these lovely photos of a fragmented comet, which are still nice in their own right, but I can't go outside and actually take a look at them. So as disappointed as I am, this will be my final word on this comet. Okay.
Yeah. That's it. No more coverage on Comet Atlas. Maybe there'll be others. And then there is, of course, Comet Swan, possibly. But Katrina was just saying in the chat that Alan Dyer has been saying that it's disintegrating too, possibly, or at least dimming.
Oh, interesting. Okay. No, I mean, it's not an uncommon thing for comets to break up as they approach the sun, right? They go on these really long elliptical orbits where they start out in the vast cold of outer space and get right up close to the sun, where the sun's heat is blasting them apart anyway. So it's more, I think more often than not, unless the comet's really large and well-lived, it's going to disintegrate.
That's true. Katrina, who is a Toronto Centre member, she just mentioned in the chat that the sun is a comet bully. And I like that description.
It also helps us see them, but yeah, it basically just destroys them.
Yeah, it helps to see them because it's slowly destroying them.
Yeah.
Well, things are a little slow in space news, and Ryan was chatting about this earlier too. It's likely to do with the fact that a lot of our telescopes are shutting down, or a lot of the bigger telescopes are shutting down, because of course they require staff to keep them running, and we're in a time where you can't be coming into contact with lots of people. So many of the telescopes are shutting down. I believe the one in Antarctica is still running, but that's because they're all isolated with each other anyway.
They are as socially isolated from the rest of the world as I think you can be. So I don't think they were worrying too much about the pandemic as much as us city dwellers are.
I don't know.
They have bigger problems.
Yeah, I was gonna say, I don't know if I'd take Antarctica over Toronto, but yeah.
It's a different set of problems, right? Your toilet water freezes solid, but at least you don't have to deal with a pandemic.
Yeah, there's that. All right, so I think that we should jump straight into talking about Mars now, because Mars is cool, and I'm excited to hear about the research that Charissa does. So Charissa, I'm gonna hand things over to you. If you can share with us a little bit about the stuff that you do, that would be wonderful.
Yeah, for sure. So I might as well share my screen. I got a little presentation for everyone to look at.
Yeah, please do.
Let's see.
Perfect. There we go.
All right. Is that the right screen? Sometimes it shares the other one versus this one. But
no,
looks good to me.
All right. So welcome everybody. I'm so excited to be here to kind of discuss Mars, what I do with it, and all that kind of stuff. And I do work with the Curiosity Rover, and it's a wonderful little robot, big robot that we are still doing operations with, even with the virus here, as a lot of operations are still remote, including what I would do. So we're able to still truck along on Mars and see what we can image and that kind of stuff. So before we kind of get started with exactly what I do, I need to give a little bit of a background. Like, for example, the seasons on Mars. Mars actually does have seasons, like Earth does. And it's basically coupled between the obliquity, which is the tilt, and then the orbit of Mars, which is actually quite elliptical. So the planet is a lot closer to the sun in perihelion versus aphelion, which can cause a lot of different temperature changes, which causes these seasons. And therefore on Mars, we have two seasons, dust and cloud. So first, I'll start with the dusty season. This occurs during perihelion when Mars is closest to the sun. This is when we get like dust devils. Primarily on Mars, a lot more dust in the atmosphere, as you can see in the two GIFs. These dust devils are actually large enough to be able to be seen by orbiters in space. So you can see in that top image there. They're usually they can range from about 1 kilometer in diameter to tens of kilometers high, so quite large compared to the ones here on Earth. And we do image them with the Curiosity Rover as well. So right now on Mars, we actually are just entering the perihelion dust season. So we are taking more movies looking for dust devils and kind of watching the dust move into the crater and whatnot. Another unique feature about this season is dust storms. Like here we do on Earth, like in Arizona or Australia. Enough dust can be kicked up into the atmosphere to cause regional or even global dust storms. Now, we did have a global dust storm in 2018, as you can see in the image there, kind of started in one area, enveloped a little bit more, and then completely covered the planet. And you can actually observe these global dust storms from Earth, from a telescope. You can see how much it opaques the surface. And basically all you can see is the volcanoes kind of poking out through the dust storm, which is insane. And we were lucky enough with Curiosity to be able to capture this global dust storm occurring, as you can see in the bottom GIF there. Basically, that's as much dust coming into the crater, and we were able to see the crater rim in the beginning, and that's what we would normally see. And then eventually it just got so red and so opaque that you couldn't see the crater rim anymore. And it was actually very interesting on operations, as a lot of different lighting effects changed how we had to operate. And it was very interesting. I think it was one of the first times we were able to do a lot of science during a global dust storm. And that's because Curiosity is powered through nuclear, right? So not solar, which is unfortunate for poor opportunity. As you can see in the top image there, that's kind of the progression of the sun being slowly blocked by the dust. And in the final panel there, the sun is there. It's just so opaque that you can't see it at all. And unfortunately, since opportunity is solar powered, this did cause her to unfortunately be declared dead. And so this kind of also helps advocate for what we need to study with global dust storms, because if we want to send humans there, we need to make sure it is a safe environment. And if we can't see the sun, then perhaps we need better sources of energy to continue on. So now kind of done with the dust season. The cloud season is the one that I am more familiar with, as this is what the work I do. So during aphelion, when Mars is furthest from the sun, atmospheric temperatures can actually get cool enough to cause what little water ice there is on Mars to condense onto dust particles, revealing clouds. It is an equatorial feature, as you can see in the Hubble Space Telescope image. And so it primarily stays in the equatorial region. And the Mars exploration rovers like Spirit and Opportunity was able to capture these clouds quite frequently, especially during the season. And we do that with also Curiosity. Now, before kind of moving on with kind of what I do, I like to always bring up the Phoenix Mars lander. Canada did help a lot with Phoenix. We had a meteorological station developed here in Canada, which include a LiDAR. What LiDAR is it's like radar, but with laser light, which pulses up into the atmosphere, and you can actually measure cloud altitude, and you can actually see precipitation from it. That's what these two images here in the top show. It shows you which altitude the clouds are at based on the particle size of the clouds. Since particle size for water ice are bigger than dust size, you can see that a larger particle size would be denoted a cloud versus dust. And they even saw like what they believe is to be snow, very faint snow falling from these clouds really early in the morning. On this station as well was also a wind indicator, pressure and temperature. And we were also able to capture images with Phoenix to show clouds in the bottom GIF here. And they were actually also able to see frost on the surface once they dug a little bit, which was very interesting. Now note, the reason why we're able to study the clouds and water so much on Phoenix was that it was landed in the North Pole, so where temperatures are always cold, so therefore water ice is more easily attainable in that region. So moving on to Curiosity, my favorite robot, obviously. Curiosity has been in Gale Crater since 2012, so quite a while. And it has kind of two main science theme groups associated with it. One is geology, which is its main use. And you can see they do a lot of drilling with geo to try to figure out the rocks. And then you see these little dots here above the drill are from ChemCam, which uses a laser and basically pews at the rocks, and then they can measure the different elements in those rocks. Now, more importantly for what I do is the atmospheric and environmental group, ENV. You can see in the bottom here, we're looking for dust devils. And that's kind of what we would do is, and what I do specifically is advocate for observations that would look at the environment and atmosphere, such as dust devils. Moving on to kind of like what I do specifically. So I'm in charge of the atmospheric movies with Curiosity. They're taken with the navigation cameras, which kind of sit just under the head of Curiosity. Two movies that we currently do take is the Zenith movie, which basically takes the head and points it directly up. And then you can view clouds overhead. And then a Super Horizon movie, which kind of takes it more towards the crater rim, which allows us to see different morphologies in the clouds and kind of what the shape is like. Now, these are movies. I've said these are movies, and if you look closely, you can kind of see that there is something in the background. However, because the Martian atmosphere is so thin compared to Earth, we actually have to use an imaging technique, use it known as mean frame subtraction, wow, which basically takes movie and creates an average frame, a mean frame, and then subtracts that frame from each individual frame. And what that does is it pulls out changes in the movie. And so therefore you can see the clouds. As you can see, it pulled out a lot more features within those movies that we would have otherwise not seen. So kind of what have we done with the Curiosity Rover? We've actually measured a lot of different properties of clouds. For example, opacity, which is the thickness of the clouds. One of my colleagues, Jacob Close, published a paper on this work, which shows higher opacity in the morning. So we would see thicker clouds in the morning versus the afternoon, possibly due to cooler atmospheric temperatures. Another thing we do with these movies is we actually monitor the diurnal or daily and seasonal patterns, like if more occurs in the morning versus afternoon, and what seasons, aka the cloud season, would have more movies that showed clouds versus the dust season. And another colleague of mine was able to measure ice crystal shape using similar movies, as you can see in the bottom here, which basically is a dome of 3 frames each all around the rover. And basically changing how you look at the clouds at different angles allows you to see different, different ice crystals based on how the sun is going through the atmosphere. So like sundogs and whatnot is kind of similar to that idea there.
Can I ask you while you're sipping water?
Yeah, go ahead.
Are there actual sundogs on Mars? Have you seen that at all?
So we have not actually yet. And this is one thing that led to her work, was wondering why we haven't seen anything like that. And so in I believe her paper said that there's different types of shapes you can see, and the shapes that she was seeing in those works would not lead to sundogs and all that kind of stuff. But it's basically there's not enough water ice in the atmosphere to cause those kind of features, unfortunately.
Darn, but still cool.
One of the interesting things I noticed is when you were showing the perihelion and aphelion of Mars, that the clouds happen closer to aphelion and in the morning and closer to the poles for Phoenix. Is that just because too much solar radiation just causes the clouds to break apart, sublimate?
That is one reason. Another reason as well is the caps on Mars have a lot of water ice in them. So a lot of clouds are more prominent near the ice caps because there's a bigger source there. But when you're traveling from the poles all the way to the equator, there's not much of a source, so they do become a lot thinner. So if you were to stand on Mars, like where Curiosity was, you'd probably not see the clouds as Curiosity would see them, as her cameras are a little slanted off of what we would see normally. So the clouds are quite thin, unfortunately for us, but that's why we use cameras, right?
Yeah.
It's amazing that Mars has so much weather, right? I mean, we've talked about snow and rain, and I remember when that announcement came out from Phoenix, and I was just blown away. I think everybody in the room was blown away. But it's fascinating. We've got dust storms. We've got these global dust storms, dust devils. So is there anything I've missed? Rain, wind, dust devils, dust storms, snow. Is there anything else? Are there secret rainbows that are happening?
We wish. Unfortunately not. It's kind of limited to, the dust storms, which a global dust storm occurs very infrequently. And so we're always monitoring the dust season to watch for one, because when it happens, it kind of can happen really quick. So you want to be able to grasp the beginning of it so we can understand it more. Precipitation wise, the only precipitation would be with what we saw with Phoenix. Other than that, we have not seen anything with Curiosity, and it's probably because of the equatorial position for sure.
Did that snow happen to land? The Phoenix snow?
I don't think so.
Okay.
I think it evaporated before it got to the surface for sure.
Okay.
Yeah.
Interesting.
But yeah,
but yet there's frost too, which is really
there is frost. So who knows? Maybe we just weren't looking at the right time, right? So yeah, but yeah, it's interesting that Mars is so quiet and yet so busy at the same time. It's really, really fascinating for sure.
Now, one of the things, a lot of the water that historically was on Mars was, I'd say the majority of it was in the northern hemisphere. Is there a relationship between the weather that we see and the leftovers of that water? Does the weather that you observe, the weather that you study, does that give us any indications of Mars's history? I know Curiosity does that for sure, but do you have any insights on that?
So if there is water in the ground on Mars, it probably doesn't evaporate enough to get into the atmosphere, basically. What happens during the aphelion season is, so the northern polar ice cap is a lot larger than the South Pole, which is maybe indicative of how much more water there was in the northern area of Mars compared to the southern. And so what happens is when that water from the caps come up into the atmosphere basically during perihelion, and then once it moves down, so it kind of travels from the north to the south. And then when the atmospheric temperatures get cool enough, allowing it to basically condense into clouds, that's why it reveals itself in the equatorial position, because it's on its way to the South Pole, right?
That is amazing. I
Yeah,
thought that's really fascinating.
Yeah, so you can see the ice caps kind of get larger and smaller based on those seasons because of how much is getting moved between the North and South Pole.
Wow, that's so super cool. We talked a little bit before we started going live about the Perseverance rover, and how is that going to build on your work? Are you involved in Perseverance at all?
So our group at York did put in a proposal for Mars 2020. Obviously, we'll be waiting a while to hear back.
Sure.
But the work that we do is very interesting because it's just with cameras, right? All we do is take images, right, of the atmosphere, and then we can pull out these different parameters you see here just from images. So basically anything that has a camera, we can use. Like the InSight lander, we're trying to see if we can see any cloud features with that. And an interesting thing between InSight and Curiosity is that they're actually so close together that you can compare what we see with Curiosity and what InSight sees to see if it's crater dependent, because InSight is outside of a crater and Curiosity is within the crater, or if there's any other patterns that are visible between the two. So that's also opened up interesting doors that we're still working with. But basically anything that has a camera, we can work magic with and then see what we can determine, right? So it's proposal wise, that sounds great. But I mean, we have to be able to explain what we can do with those images.
Now, wish list though, if you could put some piece of tech on Mars that would most greatly benefit your work, what would you put? Would you put just a better camera? Would you put some kind of laser instrument? What would you do?
So another project that I am working on at York is actually creating this system that you are talking about. It's basically a panoramic camera and then 3 lasers that point up, right? Because with LiDAR, you can study a lot more with the clouds. So unfortunately with Curiosity, we can't measure the direct altitude of these clouds, which is why it's estimated there. I had to estimate it based on what models were saying for the altitude compared to like the wind speed and direction. And so with lasers though, you are able to see more of altitude and that kind of stuff. So that's kind of a little project. I don't know how much in detail I can go about it, but I want to say the perfect thing would be something small that has a panoramic camera so you can see all of the views, right? And then lasers. And an interesting thing with this thing as well is it's small enough so that we're able to hopefully place it all around Mars, because unfortunately with environmental studies, you need to capture the whole atmosphere to understand how it works as a whole, right? But with Curiosity and InSight, it's very localized. So we can only really describe that particular region, right? Same with Phoenix and same with Opportunity and Wedge. It's very localized parameters. And so to be able to discuss more of how the water is to move from the north to south, et cetera, all around. And so that's kind of the idea of using something small, is to kind of span Mars with these instruments to be able to look at the dust and clouds more frequently.
Well, I mean, that's how we predict weather on Earth, right? We have satellites that look down, we can view the planet all at once. And that actually brings me to another question I had, was about orbiters. There's, I think, 3 or 4 active orbiters. Somebody will have to correct me, and I'm sure the chat will help me with that one. But do the orbiters have cameras that you can utilize to compare to the Curiosity data, to the rover data, to Phoenix data? Does that help you at all?
Oh, for sure. In my altitude paper that I had, I actually worked with Mars climate sounder data, which is on the Mars Reconnaissance Orbiter, which basically peers into the atmosphere from the side, like a limb view, and it measures dust, temperature, and water ice content within the layers of the atmosphere below that, so that you can tell at what altitude we are seeing more water ice versus not, which would point to which altitudes these clouds are at. Now, also with just cameras itself, MARSI, which is the Mars, I can't remember the acronym of that. I work so much with acronyms that I'm so used to just saying the acronyms, right? You forget exactly what it means. Mars Color Imager, I want to say. That's also on MRO. And they actually do daily maps of the planet for the reason of monitoring clouds and dust. So like if they were looking for when a global dust storm starts or a regional one, they can see the dust being picked up because they're constantly taking images around the planet. There's even a website, if you were to look MARSI daily maps or something like that. They post it, and they even have like little dots where Curiosity and Insight is, so you can see if there were more clouds during one day or not. And I've even looked at it myself to verify that I am seeing clouds or whatnot with Curiosity. So yeah, basically cool. Just cameras are the best. You can do a lot more science than people think with just a simple camera.
That's really cool. We've got a couple questions
we do.
From the chat. Do you want to say those, Jenna?
I was just going to ask Charissa if you had more things that you wanted to talk about before we got to the questions, because I get the sense that you're maybe not done your presentation.
There were a few more slides. For example, this one. This one is a really great new addition that I helped put together for Curiosity. And I was talking about altitude earlier, not being able to measure altitude with Curiosity. Well, these movies can measure the altitude of clouds. And that's simply using how fast the shadows on the mountain here move with respect to the zenith movie, which is looking straight up. So we have mapped Mars so well that we know exactly how tall Mount Sharp is, and basically distance in kilometers. So following the speed of these shadows here, which can only be caused by clouds, you can calculate a direct velocity of the clouds. And with the zenith movie, you can only create a degree per second, like an angular velocity with the clouds, simply because you need altitude to find the kilometers per second, which we can't have. But if you compare the degrees per second in the zenith movie to the actual kilometers per second in the cloud shadow movie, you can directly calculate the altitude, this is now the second Mars year we've been doing this observation. And so far, the results have been interesting, and we're able to compare it to help modelers and people like me who want to know these kind of parameters on Mars. Trying to think of what else. Oh, another interesting season. This is kind of like a mini season in the aphelion season. It kind of occurs right before the cloud season starts. Basically, when Mars is transitioning between the seasons, what can happen is after sunset, so these are taken, all of them are taken after the sun is below the horizon. But what happens is that even though the sun is below the horizon, the sun rays can still go high up into the atmosphere, revealing these clouds, which could be carbon dioxide clouds, which occur at really high altitudes, like around 70 to 80 kilometers, whereas the water ice occurs maybe between 30 and 40 kilometers. And so we're actually able to capture these last Mars year, basically these clouds occurring after sunset. And so we kind of put on our straps and like use the cameras really efficiently to capture more of these clouds. And so we're hoping to kind of move forward with that in the next season. Oh, and last but not least, another little project. As you can tell, I'm a very busy woman. I do a lot of things. And this new project is actually using, creating an algorithm using like machine learning and different steps with that between us at York University and then Curtin University in Australia, who are the programmers. And we're able to look at the atmospheric movies that I would take with Curiosity. It reads in these movies and then calculates the wind direction and then the angular wind velocity by itself. And so that we're able to, instead of taking these images and having to send them back to Earth for me to stare at and think I'm losing my mind if I'm seeing clouds or whatnot, and basically able to calculate this directly on board the rover or lander, and then able just to send the value, which saves a lot of data volume and allows us to get more data off of that. So this has kind of been a fun project. I just submitted a paper for this, basically going through the different wind directions compared to a previous paper that I have that I measured by staring at all these images and finding it manually. But yeah, it's kind of another fun little project. So we do quite a lot with these movies.
I have a follow-up question. I know I should ask the questions that are in the Q&A, but I want to ask you this now.
Yep.
How do you, so first of all, I can totally understand why you'd slowly go insane looking at these photos. Figuring out the differences between this stuff would like slowly drive you mad. How did they get that program, the machine learning, onto Curiosity? Is that just something that they send over and then it updates their software?
No, it's not on Curiosity. It's
Okay.
basically just a Python program that I have, right? And then since I already have all these GIFs, I insert the GIF into the program, and then it returns the GIF with the arrows showing where it points is the wind direction, and then the size of the arrow is the angular wind velocity. But the hope is to basically train it enough to put it on a future spacecraft to implement it. But yeah, it's basically with movies that we've already taken.
Okay, cool.
Yeah. And that's kind of all, that's it. That's kind of all that I have for slides wise, but I can leave these up for people to look at.
Those noctilucent clouds are just gorgeous. Like,
oh,
for anybody who's seen them on Earth, they're spectacular. But to see them on Mars is just next level. I'm so excited.
We were so excited about it that we were basically counting down the minutes till the images were downlinked here on Earth, so we could instantly look at it. I remember waking up at like 6 a.m. one day, being like, "Oh, the images must be ready," and you know, downloading them and then applying the mean frame subtraction technique. But even if we go back to that, the first image here on SOL 2400, that is with the mean frame subtraction technique, but these other ones are actually raw images of what you would see. So that's how strong these clouds are. They're actually not that faint. They're quite prevalent. And so it was really interesting and great to capture these clouds because we didn't have to apply techniques to see them. So as soon as they were down, like, you could instantly tell if there were clouds there or not. It was great.
So
thank you for making that point as well, that a lot of astronomical images are, I'd say most are enhanced, fixed up. So to comment on something that this is what we would likely see, we'd be able to see these with our eyes, that is spectacular. And that's really important, that we can look at something and say, wow, this is something you could actually see, instead of it being this beautiful image that we know has been processed and reprocessed and reprocessed. So of course you're still doing that, but that is just really exceptional. I really like that. So thank you for making that point.
No problem. So I'm free to take questions now. I'm sure
I've asked all of mine right in the middle of the presentation, so I'm done.
I'm sure there will be more. We have a bunch in the Q&A. I didn't want to interrupt you while you were going, unlike Ryan. And so so I have them.
I don't typically have to wait to ask my questions like all of you lovely people in the chat. So,
yeah, you have the privilege of being able to talk whenever you want to. Yeah. Okay, so there's a lot of questions about the dust storms, which I'll ask first because then we can get into more of the clouds. With all the dust swirling about, is there static discharge like with terrestrial volcano eruptions?
So there is some kind of static electricity, and even during the dust season, you can tell that there is some, because you'll see a lot of dust stick to Curiosity, right? You can see, or like to the solar panels of Opportunity and whatnot, you can literally see it stick to it. However, because we haven't had as much studies being done during a global dust storm and that kind of stuff, that's still something that we are working to study. And I'm not sure if Mars 2020 has something for that, but it's always something that we are looking for. But I do think there is some, for sure.
It seems like there would have to be, and especially as you said, I know one of the problems is that the dust does stick to solar panels and that sort of thing. That leads us into another question from, I don't know if it's Louis or Lewis, who is asking if the dust storms must be problematic when we eventually get there. And then this leads us into the discussion of the eventual trip to Mars sort of thing, which is a long one. But I guess the sort of branching question I have coming from that too is, if you're thinking about dropping the smaller cameras that get a bigger view of the sky, how would you get the dust off those lenses?
That is going to be always a problem dealing with Mars and the global dust storm. And I mean, at least global dust storms occur like on average every 5.5 years or something like that. And even then there can be greater periods between them. And so that, I think, is something that we're still trying to figure out to this day, that I don't even know if we have a problem for, right? I mean, you can have a brush, maybe perhaps brush it off, but then you have to make sure it doesn't scratch the camera or whatnot, right? So there's a lot of different factors you have to think of. And definitely moving towards like putting humans on Mars, global dust storms are a serious threat, right? Because they can block a lot of suns. You have to make sure you have power available. I mean, the winds on Mars, I think, top out at 100 kilometers per hour, like 60 miles per hour. So it's not hugely prevalent, but it's still big enough that it could cause a problem. So it's definitely something we do have to think about for sure.
Do you know does Curiosity have any way of cleaning its cameras?
Pardon?
Do you know if Curiosity has any way of cleaning its cameras?
Oh, I don't think so per se, like something specifically on Curiosity for it. Sometimes we can shake the head to shake off any dust. But other than that, I don't think so.
A little bit of head banging.
What a very what a lovely anthropomorphic image of Curiosity. Yeah. Can it do it while it plays itself happy birthday?
Yes.
Yeah. And I think that's it for the dust questions. So moving on to atmospheric cloudy questions. How would more water in the atmosphere affect the weather, do you think?
Well, more water would mean more clouds, right? So you'd have a more prevalent clouds being seen. Maybe you could see it more with the naked eye rather than having to use different cameras to see it. However, since there is such little water on Mars, we unfortunately can't have that. Now, more water in the atmosphere could also affect the ground, right? So perhaps precipitation could occur, that kind of stuff. And it's probably a cycle that would happen where, more water in the atmosphere would fall to the ground and then get evaporated, and then it's a huge cycle, right? So, yeah.
It's kind of like our own Earth, except, a lot less water. Yeah. So we have noctilucent clouds on Mars. And I hope I'm pronouncing that right. Is that the right pronunciation?
Noctilucent.
Sounds good to me.
Noctilucent. Good. Okay. Sometimes I only ever read astronomical things, and I find out embarrassingly late in the game that I've been pronouncing it wrong the whole time. For example, sidereal motion, which I pronounced sidereal.
Sidereal. Yes.
Yeah.
I remember those days.
Yeah, that was an embarrassing one. So there are noctilucent clouds. Do you use any analogies, analogs of Earth clouds, like cirrus clouds or anything like that? Do you end up using those analogies, or do you end up creating your own, different names for the clouds that are not related to Earth?
So with most Mars research, even with geology, we usually always compare to what we see here on Earth, right? So a lot of geology is based on that, and that's why we think Mars used to have water, is because you can see rocks on Mars that we know only form from water here on Earth, and you can make that comparison. And we do that too with clouds. Like, for example, more Sirius-like clouds are probably what we would see on Mars, simply because those clouds occur a lot higher in the atmosphere and are a lot thinner. As you can see in the noctilucent clouds, those do look like Sirius clouds. Now, with Phoenix, though, because it was near a source of water, those were more cumulus-like clouds, so a lot thicker. So we do definitely make those comparisons, but in most cases, they are more Sirius-like clouds, which if you look at it, it's a lot wispier and thinner for sure.
Makes sense.
I don't think there's been a cloud. I don't know, correct me if I'm wrong, Charissa, but has there been a cloud on Mars that isn't analogous to a cloud on Earth? Like the clouds on Earth are classified by the droplet size, the altitude, the fluffiness, to use a less scientific term.
I use that term all the time.
Do you? Oh, amazing. See, that's great. So I can't imagine that we've seen a type of cloud on Mars that is any different, that wouldn't fall into those classifications. Maybe Jupiter because of its higher gravity and its extremes, but has that happened at all?
With carbon dioxide clouds, those might be considered their own type of cloud, since the clouds here on Earth are like 99%, I want to say, water, right? But on Mars, since its atmosphere is 95% carbon dioxide, there are CO2 clouds that can occur. Now, those clouds are like hazes, more like, than anything else. So, I mean, we're still comparing it to what we would see on Earth by calling it a haze, right? But they're less defined as the water ice clouds. And that's kind of how we can tell what is CO2 clouds versus water ice, is how prevalent the features are within them, as the CO2 clouds would be more hazy. So if the water ice clouds, definitely all of them are analogous to something on Earth, right? We always compare to make sure we understand what we're looking at. And most of like the research we would do before sending something to Mars would be studying something here on Earth, right? So like that project with the camera and laser I was talking about, we will be using to study fog in Newfoundland, because they're like thicker clouds, to see how we can study those, and then taking it up to the Arctic, which has more Martian-like conditions, to see how we can study the clouds there. And so a lot of Mars research would occur in the Arctic, just because that is a similar atmosphere, I guess you say.
On that note, do you do any research in Chile due to the dryness? I guess that's not really good for finding clouds, but
I have not per se, but I know there's observatories there, so there are some work, but I am not sure about Mars-wise.
Oh, okay.
Okay. All right, onward. So there was a brief question which you kind of answered, because you mentioned that the atmosphere is 95% carbon dioxide. And that was, what is the chemical composition of the atmosphere? What's the other 5%? Would it be water?
Nitrogen and argon, I believe.
Oh, cool.
Yeah.
And then some questions about, let's see how we want to lump these together. Oh, since we have the noctilucent clouds up, can Martian noctilucent clouds only be seen when the sun is below the horizon?
Yes, they are able to be seen when the sun is below the horizon.
Okay, and we have some of them here on Earth, not quite. They're usually the ones that are, oh boy, I'm a bad astronomer. Are they created by meteors? Is that what noctilucent clouds are?
I've heard that. I remember when we were seeing these clouds, which was about May, June last year, was when we were seeing them here on Earth. And I believe it was when we were traveling through something like that causes some more dust in the atmosphere here on Mars, and then creates these noctilucent clouds.
You would need, I mean, just like any other clouds, you would need some dust to condense around. And so maybe you need something meteoric to give you that dust, that source for noctilucent clouds. So I haven't seen any correlations that anybody's published, but I'm curious now because I haven't heard that before.
Yeah, and since there's so much dust on Mars, they're probably, I would say, almost more prevalent on Mars, because there is a source for them to develop on, rather than here on Earth.
Right on.
That's very cool. Something to look forward to when we eventually get to Mars. Yeah.
Oh, one more thing on the long list.
Yeah, exactly. Interesting question about what they would look like if we were actually there, because presumably all of these images are in black and white, right?
Yeah, the Mastcam one for the noctilucent clouds, that's a color imager. So,
oh, wow.
Yes, and you can actually also tell what type of cloud it is based on the color. So the carbon dioxide clouds are more blue compared to the water ice, which are white, right? So these Mastcam ones, they look kind of blue. And so we're actually not sure if these noctilucent clouds are carbon dioxide clouds versus water ice. And so we're kind of still studying them and whatnot to see. And that's where the altitude comes in, because if these altitude of these clouds are above 70 kilometers, then they are almost definitely carbon dioxide clouds, because that's the point where carbon dioxide can condense temperature-wise in the atmosphere. Okay. So now, most of these clouds would probably look like Earth clouds, white, right? Fluffy, not fluffy, kind of Sirius-like. But that's one thing that's great with the Perseverance Mars 2020 rover, is that those cameras are colored. And InSight also has colored images, which has been fun to figure out. I'm used to working with black and white with the navigation camera. So you definitely have to figure out how to use colors, because the colors are not exactly as you would think them to be. There's different wavelength peaks, so you have to kind of work with that. And that's hopefully, if we are able to get onto the Mars 2020 mission and use those color cameras, we will be able to see more what those clouds would look like in color rather than black and white, which would be fantastic.
That would be very cool. And I know there are 4 more questions, and I acknowledge your questions, but we have hit a point where we can talk about Perseverance in the next mission. And so I think now is the time that we should maybe chat about that, because that should be launching, and it's set to launch in October. Is that right?
Yeah, summer, fall. It's always changing, you know, especially with the virus going around. Who knows if the launch date will? Right. I know James Webb, surprise, surprise, has been delayed again. Because of it, so who knows, but I think Perseverance is basically ready to go. I think at this point it's been packed and is being sent to where it's being launched, and it's been tested and whatnot, so I think it's far enough along in its progress to be able to be sent still on time, fingers crossed. And I mean, with the Rosalind Franklin rover, unfortunately that got pushed because you have to have a launch window that matches with Mars, right? Or you have to wait for that period. And unfortunately that did get delayed, I think by 2 years, because you have to wait for that launch period again. So, but Mars 2020 is such a big project that I think they're really going to push for it to be launched. For sure.
That makes sense, yeah.
It's hugely important. It's not something that can wait another 2 years for the next window. Mm-hmm. And so I'm sure that they've, you know, since this pandemic stuff has come up, they've found every possible way to try and keep it launching within that window to give it the highest chance of success, so that we can get that lovely data and continue this exploration of Mars, which will eventually lead to human exploration.
Mm-hmm. For sure.
The reason for that small launch window is just because of the way the orbits of the 2 planets work, right?
I believe so. It's like the way they can optimize the orbits and use less fuel, and to be able to land where they need to. I don't know the exacts, but yeah, it's just a prime way to launch the orbiters is how Earth and Mars are together.
Okay, cool. And
if you take a look at I guess my face right now, yeah, the launch window it's when the Earth is just trailing Mars, you launch, because a spacecraft that'll launch from Earth toward Mars will be traveling faster than Mars, and as it moves out into the further orbit, it has to catch up to Mars. And so that's kind of why that's the launch window, and that correlation between Earth and Mars orbits happens every roughly 1.5 years.
So it'd be somewhere close to like ish where it is right now in your visualization. And
yeah, there you go. Yeah, time's going a lot faster in the
obviously, yes. Yeah. This is not how we
just in case somebody
that's
didn't
fair.
know.
And I definitely have more questions to do with the next mission.
Perseverance.
Yeah, I definitely did. But
so that's all color cameras, so you'll get more used to working with more colors.
I think there's 23 total cameras.
Wow.
2020, which is insane. I mean, a lot of them are not necessarily ones we could use, but 23 in total is insane. So there's got to be one that we can at least use.
Well, and that shows too that it really is a step up from Curiosity, just as Curiosity was a step up from the Mars Exploration Rover, Spirit and Opportunity, right? So and that's what we need to advance the technology, get the next level of technology there, so that we can build upon the science that's been done already. And so I'm hopeful, Charissa, that for your group and astronomers around the world, that their research will be able to be built upon with the Mars 2020, and that nobody is really left out with the good data that comes from it.
Exactly.
Well, it sounds like the engineers and the scientists who are working on it are very adaptable when it comes to finding new stuff with the rovers. Because I remember reading a little while ago, I think it was Curiosity, they rejigged the accelerometer to figure out what the rocks underneath the tires were, underneath the wheels were, based on how the wheels were bouncing.
Yeah, I remember something similar like that. I don't know the exacts, but we're very innovative with what we can do, and people are surprised in most cases that you can take something and use it to that advantage. Like Curiosity is powered with nuclear, that I said, and that's actually only 100 watts that it powers.
Wow.
And you're able to use that 100 watts to power something on another planet, and so it's really innovative for sure. it's fantastic. And even like using these images to follow shadows on a mountain on another planet to find speed, right? Like it was just a complete fluke that we found that, and then realized we can use that science to further figure out different parameters that we need on the other planet.
You got to be smart. It's just shy of 200 million kilometers away is your nearest mechanic if something goes wrong. So you not only are the team's amazing at finding ways to fix issues, solve issues, and prepare science in advance. They really squeeze out all the science that they can. And the Cassini orbiter comes to mind, right, as it took its final dive through the rings of Saturn and squeezed out more science there. And I'm sure that when Curiosity's time comes, the scientists and engineers will find every little just thread of scientific value that they can get from that, right up until the very end. And I'm very hopeful that Curiosity will last another dozen years, right? Just like Opportunity and Spirit did. We certainly know it is dust storm proof. Maybe not proof, but at least
survived the last one, which was quite a big one. So
was that larger as far as the global storms go? I don't know much about the history of the storms.
So there was Opportunity actually survived a global dust storm. 2007, I want to say, is when that one occurred, and it was able to. It still had to kind of shut down and save resources because of little sunlight. And so big wise though, this global dust storm was very interesting as it occurred actually a lot sooner than we expect global dust storms to occur. And so it kind of caught us off guard because we were like, oh wait, there's a global dust storm starting, right? And so we're really monitoring it, thinking it was just a regional one. And then it enveloped into this big one. And then fortunately, I believe it started near where Opportunity was. So Opportunity got the brunt of it right away. And because it lasted longer for where Opportunity was, that's one reason why it kind of killed her, was it was just too dark for too long. And then eventually it came to where Curiosity location is. But big wise, I think it was bigger than the rest, but I mean, we're missing a lot of science from previous global dust storms that it's hard to compare if this one was bigger and whatnot, which is why it's great that Curiosity was actually able to do a lot of science within the global dust storm. And then hopefully if Curiosity can capture another one, then we can do comparison to see if it is bigger or whatnot.
I'm gonna ask you to tell the story again. It's like my favorite story about Curiosity Rover. But when we were talking about having to be innovative in terms of fixing the rover and finding ways to keep it running, even though we're not there to fix it, I was wondering if you could maybe, if you have that story on the top of your head, tell us about its tire that it had an issue with.
Oh yeah, I believe so obviously one issue with Mars is there's lots of rocks, right? And so, and you have to make the wheels durable, and Curiosity has 6 wheels, right? So if one craps out, then you can use the other 5 or whatnot. However, you still want to try to be able to maximize what you can use with the wheels. And I believe, I don't know the exacts about it, but basically there was a rock that was like a good shape for this hole in our wheel. And so basically we were able to drive over this rock at the great time where it basically sucked up into the hole, and then we were able to still continually use it. And so, I mean, I don't know the exacts about it, but I remember hearing about that and thinking, wow, that is innovation right there, right? Trying to say, what can we use on Mars to fix Curiosity, right? And rocks are everywhere, so, you know, why not?
It's like the most engineering way to fix it. It's that like, well, that rock looks like it's about the right size. Like, let's just drive over it and see if it plugs the hole.
Yeah.
Oh, it's great. I was wondering if you could talk about how you actually control Curiosity when you're looking at clouds and that sort of stuff.
So way we do kind of like operations, it's a lot of pre-planned stuff. So it's basically, when I plan a Zenith movie, it's Curiosity would read it as a computer program type thing, and then know that it needs to look up, and then take 8 images, and then save it and send it back to us. Now, when we do plan, we have to plan like, we don't plan it and then immediately send it. You know, you got to plan it and make sure that it's modeled correctly to make sure we don't break the rover. Obviously, we don't want to do that. And so there's a lot more steps involved than people think with operations, right? It's not just a joystick on another planet, right? That's where like the Big Bang Theory gets it wrong. It's not that easy. There's a lot of different steps you have to go through and verification to make sure you aren't going to break the rover. And you also have to think of like a sun safety. So you don't want to point these very fancy cameras at the sun because it can saturate images and also wreck the camera itself. So like the movies that I take with On the Mountains, they can only be taken in the afternoon because Mount Sharp is directly east of Curiosity. So you can't take it in the morning because the sun would be pointed right where the mountain is, and that's not sun safe for the camera, right? So you have to think of various things like that, different parameters, and yeah, so it's a lot more involved. I can't go into depth too much, unfortunately. Clearance says no.
Secrets.
You know, the great thing about my work, but also kind of sad.
Yeah.
But yeah, there's a lot more steps involved. And I believe if people go to MSL Sci Corner, it goes a lot into depth on operations and how we do it, timeline, and different roles that we have for Curiosity.
Okay, cool. And I do think, I mean, that to your point about joysticks and that sort of stuff, I mean, that wouldn't work even if you know, you weren't worried about the safety of the robot, because it's a delay to getting the information, right?
Exactly. It's got to take time to come from Mars to Earth, right? So like sunlight takes 8 minutes from the sun to Earth, right? So you got to think about it like that. There is a slight delay, and so you have to time it quite well so that we're able to do the science at the exact times that we want it.
It varies between 4 and 24 minutes, depending on the orbits.
Right, because it can be on the other side of the sun.
Yeah.
And that would, you also, I mean, there's a bunch of people using this, and that's that whole working in a team thing, right? You don't want to mess up everybody else's research just for the sake of your own.
Please.
Yeah. I have a couple other questions. If you want to answer them, do you feel like continuing to answer questions? Okay, cool.
Don't go too far. We could be here all night.
That's a problem that we do have.
I've got questions you haven't even heard of before. But no, this is great. We're actually, Charissa, we're loving having you answer all these great questions, and thank you for doing all this. Let me say far too early again, because we're not done yet. But
how dare you start to close up, Brian?
I know, right? So let's keep going. Keep peppering her with these great questions so we get more great answers.
All right, cool. The cameras that you're using for the landscape stuff, so of Mount Sharp, what's the resolution of them?
I don't know the exact resolution, but the size of the navigation camera that takes them, the field of view is 45 degrees by 45 degrees, right? And so basically how I look at them resolution-wise is I take your field of view and then the size of the image in pixels, and then create a degree per pixel resolution. And that's kind of how I work with it. So if I go back to that slide,
I'll switch the views.
These ones here. So these movies here are 1022 pixels by 1022 pixels, I believe.
Okay.
And then they have a 45 degree field of view. So when you kind of change it to that degree per pixel, you can find a degree per second, essentially, by dividing out how many seconds the movie occurs from, which is about, I believe, 235 seconds is when the Zenith movie, the length is. And so you can kind of then take that also to the Cloud Shadow movie, but then actually be able to convert it to kilometers based on how far it's moving across the mountain. But I don't know the resolution of the nav cams off the top of my head, unfortunately. But that's how I would use resolution, at least.
Okay, so for those who are interested in astronomy, math is important.
Yes, SOHCAHTOA I use to this day, figuring out all of these things. So yes.
That's incredible. The thing that blows my mind about astronomy in general, because I don't come from an astronomy background, is just the amount of like thinking it takes to get to the answer that you want. This sort of like, okay, so we have these two images, one up here, one down here, and we can see shadows over here. So, okay, so then we're seeing the shadows from over there, from this thing up here, and then how fast they're moving is based on how wide the field. It's just, there's so many steps.
Yeah, the majority of the work is just figuring out the problem and what you need to have to solve it. And then it's like, results are just quick, right? So you write a computer program to go through it and do it, and then that's that. But the majority of the work is, yeah, taking what we can see and then trying to convert it to what we need, which is, yeah, the majority.
Charissa, I preached you on that one. You're saying that was the right thing. I remember when I was in grad school, it was the same thing. 95% of the work, you want to write down and tell everybody about and be like, hey, this is all the cool stuff I did to get from here to here to here and get this amazing result. And my supervisor basically said, don't put any of that in any of your presentations.
Aww.
See that last slide that you did? Make that the presentation. And I was like, oh, but it was still really fun to talk about. But it was a good lesson that, not a lot of research work. The vast majority of it is the grind, is the figuring things out, doing this, working with the numbers, working with the data. And you do get these beautiful products at the end that you can talk about, but it's oftentimes it's more that people care about the results, that 1%, that 5%, than they do about the 95% of brain work, intelligent work that you did.
Yeah. So yeah, and that's why they a master's degree and PhDs are so long. It's because you need that time to figure out what the problem is and how you're going to solve it. And then basically writing your thesis is like the last year or even 6 months, right? Of the 4 years for the PhD or whatnot, is just trying to figure out these problems and how to solve it, for sure.
Mm-hmm.
I wish that society cared more about the process and less about the final results, because I think you're spending so much more time on the process, and it's just phenomenal the amount of brain power you need to get to the end. And it's just kind of, when you look at the media looking at it, they just go, oh yeah, this thing happens. Isn't it nice?
I think a lot of that too is that science is so niche now. Like you're not just 500 years ago you were an astronomer. Today, you're a planetary scientist, a galactic astronomer, and even subfields within those categories as well. And so it takes more and more effort, better, higher resolution cameras, better imaging, better space telescopes, spacecraft, to get the data that lets us push those boundaries a little bit further. So although it is difficult and we get, I guess, less total stuff out of it, it's showing that we really are pushing and pushing and pushing at the limits of what we know. So we just, I guess, got to find the value in that.
Yeah, it's a huge collaboration thing too. Like with the Cloud Shadow movie, it was actually a dust devil movie pointed at the mountain that was looking for dust devils. That then was the guy who monitors that was like, hey, what is that? And then next thing you know, I'm jumping into chat. So I'm like, what is this? Like, oh my. And we're like, wait a minute. This entire time we could have been taking these movies at the mountain to eventually find these altitude, which is pretty much impossible without a LiDAR or this new method, right? And so it's a really good collaboration project. I mean, sometimes like in my Super Horizon movies that point towards the crater rim, I'll have a dust devil photobomb it, and I'm sending it to him, and then he has a cloud that photobombs his dust devil movies, and he sends it to me, and we're just joking. And so it's a huge collaboration thing too. You have to work together to figure out these problems, and sometimes you get these mistakes that turn into useful science, right? And this will be great science to work with, for sure.
This is just so cool. It's one of those things where when it comes to doing science, first of all, a lot of people assume it's science or arts, and you really need both to get the creativity to figure this stuff out. And the fact that you're working with people that either you may never have met or are working on completely different things, and you can still find stuff that works for both of you.
Exactly.
That's so cool.
Yeah.
Sometimes the best science doesn't come from, hey, that's what we expected. It comes from, what the heck's going on there?
Yep, exactly. Yep. A few swear words in there, like.
Yeah. The rated R version we can't really do.
Oh,
here,
no.
so,
Alrighty. I think it's 9:10. I'd say maybe, actually on the note of interdisciplinary work, there was a question from Janine about how much interdisciplinary work do you do, Charissa?
It's hard to say sometimes. Oh, sorry, I think my camera kind of froze there for a bit. So for me, I like to broaden my horizons, especially during the PhD, to, get a good job after the fact, right? And so, when I was doing work with the observatory, that could have been a lot of interdisciplinary stuff, just because it's a lot of creative things that you have to think about, and how to teach science to arts majors or whatnot, right? Because sometimes a lot of this stuff can go over people's heads and they're like, wait, what? And so it can be fun to do outreach for other people that are not necessarily science-based, because it teaches you how to describe your science in a way that everyone else can learn and study from. But right now, I feel like I'm not as interdisciplinary with this kind of work. It's very sciencey. But I'm always open to that kind of stuff, and who knows, right? Unfortunately, I'm so busy right now that it's hard to find time for anything outside of this, right?
Well, then thank you for giving your time to us.
Absolutely.
Right? That we have, you heard it here, we have Charissa Campbell's precious little free time. So thank you for that. That's amazing.
No, I'm really big with outreach. I've been doing outreach for many years, working with observatories and whatnot. And I feel like the more science that you can describe to the general public, the cooler it gets, right? Like, just trying to describe this to other people, it makes me appreciate the work that I do as well. And not that, oh, I'm just a PhD student doing science. It's like, no, I'm a PhD student doing work on Mars, looking with cameras with, a rover and whatnot. It really is fun. And it's great to see people's reactions to that, and just the awe-inspired stuff that you can generate, for sure. So I'm always happy to do outreach for my work, for sure. And yeah, thanks for having me. It's great.
I will admit that one of the reasons that I was asking Charissa to come on board was because at the GI, I spent most of it sitting with her going, well, tell me about Mars. And so she's like, you're one of my favorite people to listen to. I love hearing about the stuff that you do. And it's just so cool. Like, you get to you drive a car on Mars and you take pictures of stuff there. Like, it's just so cool.
It's surreal sometimes. Sometimes I don't believe that this is what I'm doing until, you talk to someone and they're like, holy crap, what? And I'm like, oh yeah, whatever.
I think it was like by the third or fourth time that we'd met that you mentioned this, and I was just like mind blown. Like, if I were you, I would be literally shouting it from the rooftops.
Yeah. Well, and Mars work is quite popular now, right? I like to say the second space race is just beginning, right, with SpaceX and all these companies coming out, and people want to go to Mars and they want to learn more. So this is a great time for me to get my foot into the door. And I've actually been wanting to study Mars since I was young, very young, maybe 10 or 12, and astronomy in general since I was young. My first word was moon. So it's like destined to be, right? And so the fact that I made it here and I am studying Mars stuff is just, it's amazing. I'm very grateful.
It takes a lot of hard work too, and you've clearly put in the time, and you've done so much cool stuff. This is having a very wrap-up-y tone, and I think it's at 9:15, so it may be time to start wrapping up. Ryan, do you have any last questions, or Charissa, do you have any last things that you want to talk about?
I have no other questions. I just want to say that all the amazing things that you've done, and your career is just starting. Like we can't wait to see what other things that you do soon in the future and in the distant future as well.
Yeah, for sure. It's just starting, and it's crazy to think that, because I've already done so much work and I've got so much work ahead. But that's something to look forward to, is how much more work can I be involved in and really help out with. And it's going to be fantastic.
I have one final wrap-up question. If you could go to Mars yourself, would you go?
That is a question I get a lot. And yes, actually, I think I would. I mean, of course, it's a one-way trip. And I mean, we will eventually get to the point where it's two-way. In my opinion, why wouldn't you, right? Why wouldn't you want to invest in getting there and learning more about it? I want to see these clouds through my actual eyes, right? So
Absolutely.
yeah, so I think I would. I mean, the competition's tough, so I probably never will, but you can always dream.
You can always dream. And on that note, I was talking to my brother about the whole like commercial astronauts who are going up. When I was a kid, nobody told me you could be a commercial astronaut because they didn't exist yet. So you never know what might come up.
Exactly. Yeah, it's always changing.
Mm-hmm. Thank you again so much for coming. We're so happy to have had you, and thanks so much, Ryan, for all the great questions. I'm just so excited. I'm so glad that you were on. We'll catch up more later, Charissa, you and I offline.
Of course.
And
thanks for having me.
And thanks everybody for joining us. I was going to wrap up with a couple things that you can see tonight. If you have the time, I'd recommend running outside right now and taking a look at the full moon, which is the last supermoon of, well, tomorrow it will be the last supermoon of 2020, and Venus, which is still up. If you want to see Mars, you have to get up at like 4 a.m. But it will be starting in October. It'll be really close to us. It'll be at its closest opposition, and it'll be big and bright in the sky, and it'll be seen right after sunset. So that'll be in October. Keep your eyes open for that. And thanks again, Charissa, for being here. And we'll see you guys soon.
Yep. Thanks for having me.
Take care, everybody.
Thanks a lot, Charissa. Good night, everyone.
Good night.
Bye.